Alright guys, so let's look at some basic calorimetry problems. So we're going to be measuring heat transfer within a system. So here's a typical specific heat problem we can come across. So here it wants to know how many joules of heat are needed to raise the temperature of 10 grams of aluminum from 22 degrees Celsius to 55 degrees Celsius. And it says if the specific heat of aluminum is 0.90 joules per gram degree Celsius. So anytime we are increasing temperature and we're not going through a phase change, that is where we're using the formula. It's Q equals MC delta T. So that was one of your formulas from Chem 1 that we used. And that one is one that we'll use yet again when there is not a phase change. We are just increasing temperature. And I'm trying to confirm if that is on your reference sheet. It is not on your reference sheet. So that is one that you need to be able, or it is on your reference sheet on the second page of equations under thermodynamics and electrochemistry. It is that first equation is the Q equals MC delta T. So Q is referring to heat. That's going to be measured in joules. M is going to be your mass. C is your specific heat. And delta T is your change in temperature. And wherever we're doing our change in temperature, as with the previous video, you always do the final temperature minus the initial temperature. That way you have it noted if the temperature change is positive and increasing or negative and the temperature is decreasing. So plugging in values that we know, let's know how many joules, that is Q. So we're solving for Q in this case. Tells us that our mass of aluminum is 10 grams. Our specific heat for aluminum is that 0.90 that's given. You're going to be given specific heat values. You don't have to memorize them. But they are not given on your reference sheet like they were in Chem 1. And then our temperature change, we're going from 22 to 55. So you flip them and do the final temperature minus the initial. You can also subtract that, so that would be a difference of 33. And you could plug in 33 in its place. Notice with temperatures, like it didn't give us decimals, but remember we do go to like the whole number if there's no decimal place. So like this would have 2 sig figs. So then we have to multiply those numbers together to solve for Q. So 10 times 0.9 times 33 is 297. And that is joules. Sig fig wise, so 10 has 3 sig figs, 0.90 has 2, 33 has 2. So we need to round this to 2 sig figs. So that would round this up to 300. However, that is not written with 2 sig figs. So we need to denote that that's 10's place is where we rounded to. So this is a case where it's going to be smart to put the number in scientific notation. So 3.0 times 10 to the second. And that is joules. So anytime you're trying to like change your number of sig figs, you can also use scientific notation as an option. Let's look at another example. Here it says it takes 487.5 joules to heat 25 grams of copper from 25 degrees Celsius to 75 degrees Celsius. What is the specific heat in joules per gram degree Celsius? So yet again, we're not changing phases or anything like that. We're still using the Q equals MC delta T. It gave us our joules, which is our Q, so the 487.5. It told us our mass was 25 grams. We don't know specific heat, that's what we're solving for. And then our change in temperature, it went from 25 to 75. So you can do the 75 minus 25. Or you can go ahead and say, well, that's going to be 50. One thing to note is this, we know that one's place. So this would still be the 2 sig figs. So here to solve for specific heat, to solve for C, we have to divide. So 487.5 divided by 25 divided by 50, and we get 0.39. And 487.5 has 4 sig figs, 25 has 2, 50 has 2, because we know that one's place is exact. So 0.39 is 2 sig figs, and our unit for specific heat is that joules per gram degree Celsius. So you should be able to use this to solve for any variable, whether it is mass, change in temperature, or even the final or initial temperature. It's all about manipulating that base formula of the Q equals MC delta T whenever we are not going through a phase change. So how this changes is whenever we go through a phase change, we're now going to look at a heating and cooling curve. This is something that you saw in Chem 1. This compared the energy changes as temperature changes within a system. So it did have this zigzag pattern to it. Notice that the lowest temperatures down at the bottom left, the substance is a solid. Once it reaches a certain temperature, it is going to convert and melt into a liquid. While it is melting or freezing, either time, that is a phase change. The temperature is constant during a phase change, so it's a flat line. And the amount of energy needed for it to melt is our heat of fusion. One thing to note that is going to be different from Chem 1. Chem 1, all of our stuff was in joules and we used mass for everything. Your heat of fusion value is going to be given to you in kilojoules per mole. So we will have to change grams into moles, and our final answer will be in kilojoules. So I'll show you how to handle that in a moment. Once all of the substance is a liquid, the temperature starts rising again until it reaches a certain temperature, which is the boiling point, and it will boil or evaporate and change into a gas. That value of the energy required is our heat of vaporization, yet again given in kilojoules per mole. And remember we talked about with intermolecular forces, this value is much larger because we are actually breaking apart those intermolecular forces versus weakening them. So it takes more energy to completely break those forces. And once all of it changes into a gas, the temperature can then go up again. And this works heating, reading it from left to right. This also works cooling, reading it from right to left. One thing to note, if we are cooling, it is losing heat instead of gaining heat. So the heat of fusion and heat of vaporization values are going to be the same number, but negative if we are cooling the system down. You don't have to memorize any of the constants of specific heat or heat of fusion, heat of vaporization. The only one you should know is in the liquid stage. Specific heat for water as a liquid is that 4.18 joules per gram degree Celsius. That's the only one that may not be given to you, but all the others will be. So it will be using values that are given appropriately within the context of the question. Typically we're going to be doing these with water, but you may be asked to do this with another substance like ethanol or something, but you would be given all the values. Remember the temperature boundaries here for water is that freezing and melting occurs at the 0 degrees Celsius. That boiling and condensation occurs at 100 degrees Celsius. So like a solid cannot get any hotter than 0 degrees Celsius. Liquid is only going to exist between 0 degrees Celsius and 100 degrees Celsius, whereas a gas is not going to exist until the 100 degrees Celsius and above. So if we're going from like -10 up to 110, we're going through every single line. So each line segment in this curve is going to be a different problem. So how we're going to use that is, let's look at this problem. Here it wants to know how much energy is required to turn 75 grams of ice at -20 degrees Celsius into steam at 100 degrees Celsius. So you first have to figure out like what steps you need to go through. So I tend to draw a quick sketch of a heating and cooling curve. And I like to mark kind of my starting point and my ending point. That way I can see what steps I need to go through. So remember, our first flat line was at 0. Our second flat line is at 100. So if we're at -20, that's down here below 0 in the solid phase. And if we're changing into steam, which is a gas, at 100, that is the flat line at 100, but on the gas side of it, at that corner. So if we're kind of connecting all the dots, we have to heat up our solids. We're going to have a solid step. We have to change from a solid into a liquid. So that's going to be another step. Then once everything's liquid, it has to heat up to 100. And then once 100, it will change into steam, also at that 100 degrees Celsius. So that's a liquid to gas stage that's occurring. So this is going to be a 4-step process for us. We did go over whenever it is a single phase and the temperature is changing, you can use that Q equals MC delta T. So that is just a specific heat problem whenever the temperature is changing. However, we cannot use that formula whenever we're going through a phase change because the temperature does not change during a phase change. So there's a separate equation to use for phase changes, and this one is not on your reference sheet. This is going to be Q equals N delta H. So Q, yet again, is heat, so that's joules, or kilojoules. N is moles. So that's where I said we will have to change from grams into moles. And your delta H, a lot of times, is going to be given in kilojoules per mole. So this equation is going to give us an answer in kilojoules, whereas using specific heat, we tend to get our answer in joules. So the first equation, the Q equals MC delta T, is used whenever it's a single phase. It's like a solid, liquid, gas, and the temperature is changing. The Q equals N delta H is used whenever we are going through a phase change, those flat lines, and the temperature is not changing. So let's look at solving these. First step we said we have is the solid step. We're starting at -20, and we have to heat up the solid, and solids only go up to 0. So we're changing temperature, so we have to use that first equation, the Q equals MC delta T. Our mass, we said, was 75 grams. C, specific heat for solid, will be given to you. For ice, it is 2.05 joules per gram degree Celsius. And then our temperature change, like we said, it is going to go up to 0 from -20. So we would calculate that step individually. So we have 75 times 20 times 2.05. So this step alone is 3,075 joules. And I'm going to come back and look at sig figs and units in a minute, because you'll see we have to do a little something extra with them. So that got me to this first corner where we have a solid at 0 degrees Celsius. Now that solid has to melt into a liquid. So this is a flat line where the temperature is not changing. So we have to switch to that Q equals N delta H. So for N moles, the problem did not give us moles, but it gave us grams. So we can take the 75 grams and use molar mass to change into moles. So remember, ice is water. So water's specific heat, molar mass is 18.016 grams per mole. And by adding that conversion in there, we change to moles, which is going to match up with the rest of our units. For delta H, like I said, this will be given to you. And going back to our other equation, or our other page, heat of fusion, that delta H going between solid and liquid, is going to be 6.01 kilojoules per mole. So then we can do the math there. So we have 75 divided by 18.016. That gave us moles. Multiply by the 6.01 kilojoules per mole. And this gives us 25.019 kilojoules. And like I said, I'm going to come back and do sig figs and check units in a moment. So that got us to this corner where we are still at 0, but now we are a liquid. So once everything is a liquid, the temperature of that liquid is going to heat up to the boiling point to 100. So since the temperature is changing, we go back to the Q equals MC delta T. So our mass is 75 grams. See, that specific heat for liquid water is that 4.18 joules per gram degree Celsius. And our change in temperature, the liquid is starting at 0 and going up to 100. So it's the 100 minus 0. So we have 75 times 4.18 times 100. This is 31,350, and that is joules, to match up with our specific heat. And yet again, I'll come back for sig figs and units in a moment. So that got us to a liquid at 100, where it is going to start boiling and changing into a gas. So we have to change our liquid into a gas. So it's a flat line, the temperature is not changing, so we have to go back to the Q equals N delta H. Our N moles, you can use the same conversion you had up in the solid to liquid stage, so you can either calculate it or just copy that conversion back over. So it's going to be the 75 divided by 18.016. And then for our heat here, this is heat of vaporization, goes between liquid and gas. So if we go back to our heat and cooling curve, the heat of vaporization for water is 40.65 kilojoules per mole. And yet again, that value will be given to you. You don't have to memorize it. So we do the 75 divided by 18.016. That gives us moles. Multiplied by the 40.65. And this step requires 169.2 kilojoules. Now, typically what we do is now we add everything together to get the total amount of energy that this requires. However, notice that we did not do sig figs, so we have to go back and do that. But we also have some of our units are in joules, some of our units are in kilojoules. So before we can add them, they have to be in the same unit. So typically I change everything into kilojoules. That way it's a more reasonable number whenever I add. So looking at the solid set, in order to change it to kilojoules, we will need to move the decimal 3 places. Sig fig wise, 75 had 2 sig figs. The temperature, 20. Remember, we use the whole number when there's no decimals. That also had 2 sig figs. So this rounded to 2 sig figs is going to be 3.0 kilojoules. And here's where, because rounding might be slightly different, there is an acceptable range. Oh, excuse me, that's 307, so that's 3.1 kilojoules. It will round up. The next one, solid to liquid, is already in kilojoules, but we have to take into account sig figs. 75 had 2 sig figs. We tend to not use those constants. It's like 6.01, so we would base it off of the 75. So if we round this to 2 sig figs, it's 25 kilojoules. For liquid, yet again, it's in joules, so we would need to move the decimal 3 times to change into kilojoules. 75 has 2 sig figs. 100, whenever we include that ones place, will have 3 sig figs. So yet again, we need to round to 2. So this will be 31 kilojoules. And then our last one, we had 2 sig figs with 75. So if we round this to 2 sig figs, it's going to be 170 kilojoules. And then we add all of them together to get that overall total. So if we have 3.1 plus 25 plus 31, excuse me, my calculator is not on. So 3.1 plus 25 plus 31 plus 170 is a total of 229.1. And that is kilojoules. However, remember, adding and subtracting, you go to the least number of decimal places. 3.1 has 1 decimal place, but 25, 31, and 170 are all whole numbers. So if we round this to a whole number, it's going to be 229 kilojoules. And this was a fairly long problem because we were going through 4 of the 5 possible steps of either heating up a phase or going through a phase change. Some problems are going to be shorter, where maybe you're just doing a phase change or just changing the temperature for one section, but using the little graph does help you ensure that you don't skip a step. So some takeaways and things to remember. Temperature is constant during a phase change. So all of the energy is going to weakening or breaking those intermolecular forces. So if temperature is constant during a phase change, you have to use that Q equals N delta H formula. There's no temperature change. So if you tried to use Q equals MC delta T, you're going to get 0, simply because that temperature does not change. With endothermic and exothermic reactions. So remember, endothermic reactions are absorbing heat. So all of the Q values are going to be positive because you're gaining heat through each step. In an exothermic reaction, you are cooling and releasing heat. So all of the Q values will be negative throughout the course of a reaction. And overall, with calorimetry, energy is conserved. So whenever water is absorbing energy, that energy just doesn't come from nowhere. It has to be like on a hot plate where it's absorbing thermal energy from the hot plate into the water. It simply is converting from one type into another.